Hello and welcome again to my Physics Online video lecture series. In today's video, I'm going to be talking about a sort of class of problems that you can encounter in kinematics. They are in some sense classed as 1D kinematics problems, and in some sense they are 2D kinematics problems in as much as they are sometimes introduced after you learn about relative velocity. In today's video, I'm going to be discussing them in the context of just knowing 1D kinematics, not knowing anything about relative motion or relative velocity. I may make a future video in which I revisit these in terms of relative motion. So these types of motion are what are called chases and races. And the basic idea is that they involve two or more moving objects or people, and usually moving towards the same endpoint, or one is trying to catch up with the other. In the case of a race, you could have more than two, obviously, but in a chase, typically you just have two objects. They are good kinds of problems in 1D motion to really test your problem-solving abilities, because rather than just being able to use the equations that you've learned so far and just plug and chug and get an answer, you have to do a little bit of problem solving, a little bit of interpreting the information you've been given, but for two different things, and therefore keeping track of two equations and figuring out how to reconcile those two equations, or more if you happen to have a race with three or more participants. So here's the basic type of problem. Either you have two or more people racing each other. Typically with two, you'd have one person initially with a head start, possibly also a greater initial speed, and then the other person ends up having either a greater initial speed and is lagging, or maybe they have the same speed but they're accelerating, or maybe even a lesser speed but they're accelerating, or they have a greater acceleration. So basically, one person has sort of the advantage in one or more parameters, and the other person has the advantage in at least one other parameter. And so what separates a race from a chase? Well, as I said, in a chase there's typically two people. In a race there might be more than two, but often there's still two. The usual real difference between them is that if there's a chase, one person is sort of trying to catch the other, and if there's a race, there's usually a finish line that both are trying to arrive at first. Okay, so in some sense these two problems are very similar. Usually what's asked of you in these two types of problems is slightly different though. In a chase, the typical question is when or where, so at what time or at what location or position, does the person who's lagging behind first catch up with or pass or whatever the person who's initially in the front? Okay. If it is a race, there's sort of three questions that are often asked. One is who gets to the finish line first, although that's usually the least exciting question from a if you're taking this course and expecting to see it on a quiz, because there's three options: racer 1, racer 2, or they tie. But the two more interesting questions are who gets to the finish line first and by how much distance, or who gets to the finish line first and by how much time. So for this video, a lot of what I want to do is walk through the basic problem-solving strategy more so than try to work a lot of examples, because examples typically take a lot of time, and I do want to keep this as a relatively short video. But I will give a sort of information kind of thing that you might see an example and then walk through how I go about solving it. So suppose that you have a race. Suppose that you're told that you have two racers in the race. Alright, suppose that you have a race. Suppose that you're told that there's two racers at the front of the race. and one of them has a head start of 7.5 meters and holds a constant speed of 6.5 meters per second. The other one has a slightly slower speed, 6.2 meters per second, but they put on a sudden burst of speed as they see the finish line. So they kind of accelerate by 0.2 meters per second squared for 2.5 seconds, after which they're presumed to just maintain a steady speed. And we're told that the finish line is initially 35 meters from racer number 1. Okay, so maybe we're asked by how much time or how much distance does one of the two beat the other? Who wins and by how much time, let's say. So how do you go about breaking down this problem without using relative motion? Well, what I'd like to do is kind of find two sets of equations. And what I'm going to do, I'm going to make a green set and I'm going to make a purple set here. So racer 1 will be kind of the purple set. Racer 2 will be kind of my green set. Okay. Now the information that I see that goes with racer 1, there's a 35 meter distance to the finish line, and they have a constant speed of 6.5 meters per second. Okay. So in some sense, you can figure out immediately how much time is left before racer 1 gets to the finish line. Okay, it's a very straightforward process. Basically, we need for delta x1 to be 35 meters. And we know that delta x1 is going to be the speed times the time. Okay, so that means that the time that he's going to need to get there is going to be delta x1 divided by v1. So that is 35 meters divided by 6.5 meters per second. And you can put that into a calculator to get an amount of time. So 35 divided by 6.5 gives us 5.3846. So that is 5.3, let's call that 5.38 seconds. Okay, what about runner number 2? What does runner number 2 see? Well, delta x2 is not 35 meters, but rather 35 plus 7.5. So that is 35 meters plus 7.5 meters, or in other words, 42.5 meters. So in some sense, we got to underline both these things for runner 2. We're also told that he has an initial speed here and then an acceleration for some amount of time. Now this problem would be a lot easier if we were just told he accelerates like this for the entire time until he hits the finish line, but that's not how people usually kind of take the last lap of a race. They don't usually get to just keep accelerating and accelerating. Usually they can put on a sudden burst of speed and that's about it. We may even be pushing it by saying they get 2.5 seconds of acceleration, although I did give them a relatively low acceleration for that 2.5. What I would do here is actually break this into two pieces. Okay, piece number 1 is 2.5 seconds. Piece number 2 is for wherever he is after that much time until the finish line. And so the first part you have a constant acceleration, the second part you have constant speed. And so basically for the first part, what you would have is something like, let's call this x2 first part. And so that would look like x2 initial plus v2 initial times time plus 1/2 a2 times squared. And we're using t equals 2.5 seconds. We're using x21 to be, or x2 initial to be this 45 meters, except for we're going to make it actually negative. So negative x2 initial. Why are we making x2 initial be negative 42.5? Because they are that far behind the finish line. They're moving towards the finish line, so v is positive, a is positive, delta x initial would be therefore negative in this case. Okay, so that's negative 42.5, and of course v2 initial is your 6.2 meters per second that he has initially. Okay, so in some sense that means that the position x21 is negative 42.5 meters plus 6.2 meters per second times 2.5 meters plus 1/2 of 0.2 meters per second squared times 2.5 seconds squared. So that goes into the calculator. Whoops. Minus 42.5. Alright, and so that's how far Racer 2 still has to run after those first 2.5 seconds. You also need to update the speed. So update speed. And the new speed, v2, is equal to v2 initial plus a2 time. So that is 6.2 meters per second plus 0.2 meters per second squared times 2.5 seconds. Okay, so these two multiplied by each other gives me 0.5, so I end up with 6.7 meters per second. Okay, so now we're ready for the second part. So for the second part, we can say something like delta x2. So this is negative of delta x2. We're basically now modeling it as a constant speed, which is how we did the purple equation for x1. So we should basically just do the same thing we did for x1. It's just that our time is going to have to be added to this 2.5 seconds here. So delta x2 is 26.375 meters, and that is equal to v2 times t, or if you want to call it t prime or t2 or whatever you want to describe it as. So if you want to keep track of stuff by calling this all T1 or something, or T21, and then the bottom one could be T22, then essentially what you end up with is that T22 is delta x2 over v2, and that's 26.375 meters divided by 6.7 meters per second. So throw that into the calculator, divided by 6.7, and what we get is 3.93. So this is about 3.936. So let's call it 3.94 seconds. So now we ask, what's the total time? So total time T2 becomes T21 plus T22, which is 2.5 seconds plus 3.94 seconds, which comes out to 6.436, so 6.46 seconds. Okay, so conclusions. Racer 1 wins. The difference in time between the two, this would be basically T2 minus T1, 6.46 seconds roughly, minus 5.38 seconds, so 5.38 seconds. So plug that in. You get that 1 crosses 1.06 seconds ahead of 2. You can also figure out the distance. You can also find the distance by multiplying that time that we've just found by subtracting the two times from each other by the speed that the loser has, that number 2 has in this case. And so for that you end up getting 7.08 meters. So you could conclude that Racer 1 wins. He wins by 1.06 seconds approximately, and racer number 2 still has 7.08 meters to go when racer 1 crosses the finish line. So this is the basic process for solving these kinds of problems. Essentially what you do is you split them into two sets of equations and solve given your endpoint conditions. Alright, so that was races. Now we might ask, what do you do differently if you're doing a chase? And so in a chase, typically you're trying to find when or where the first person catches the second. And so what changes in the problem-solving approach is that instead of two sort of separate equations that you're solving for an endpoint, you now have a system of two equations with usually two unknowns. The approach takes a few steps. So if we go back to the two racers and change them into chasers, so we call them runner 1 and runner 2, and use all the same information. The only new information that's missing is there's no finish line. They're just running in a straight line for whatever reason. Maybe they're actually in cars or something on a road and they're going in a straight line because the road is straight. Speeds are wrong for that, but whatever. They're running in a straight line. One of them still accelerates briefly before hitting a top speed, then they just kind of like cruise at their top speeds until one catches the other. So there's no finish line. The question might now be, when and where does one catch the other? So for this kind of problem, we have a slightly different approach. We will need to kind of update information for both rather than just for one or the other. So let's again look at what information we have. Essentially, we have runner 1 who has this initial speed and some head start. I'm actually now going to include the head start as runner 1 information rather than runner 2 information. And then runner 2, who I'll again do kind of in green. I'll kind of double underline it here. You've got 6.2 meters per second and then also this acceleration. Okay, so in some sense, again, we have to do a two-part. Part 1 is when runner 2 is accelerating. Okay, so this is essentially a delta t of 2.5 seconds for both. And so for both of them, we can say delta t is 2.5 seconds. And so we might call this like t 21 and t11. So t11, t21. And what we want to do is figure out where are they both located and what is their speed at the end of this 2.5 seconds. So runner 2, we could call this x21, just has this constant speed. So we have v21 times t21 and so plus the initial, so plus 7.5 meters or plus x11. Okay, so that becomes 6.5 meters per second times 2.5 meters plus 7.5 meters. You throw all that into our calculator, 6.5 times 2.5 plus 7.5 gives me 23.75 meters. This is about 23.75 meters. Okay, and of course V22 is just equal to V21 because there's no acceleration. For the green, we have X, let's call this X2, this first one was X1. X21 is 1/2 A2 T21 squared plus V21 T21. Okay, so that is 1/2 times your 0.2 meters per second squared times the time, which is again 2.5 meters per second, 2.5 seconds squared. plus the initial speed, which was 6.2 meters per second, times the time, which was again 2.5 seconds. So that goes into the calculator. So we have 2.5 squared times 0.2 times a half plus 6.2 times 2.5. That's 16.125. So x21 is 16.125 meters. Okay. V22 needs to be V21 plus A1 T21. So that is 6. That's weird. That is 6.2 meters per second plus whatever the acceleration was, so that is 0.2 meters per second squared times 2.5 seconds. So V22 again is 6.7 meters per second. Now we're ready to do this. For the second part, both are now moving with steady speed. The first one should look like this. X12 should look like X11 plus V12 times T12. Okay. And the green guy, X22, should now look like X21 plus V22 T22. Now here's where the trick comes in. We know that we're looking for the time and or location where number 2 catches up with number 1. Mathematically, that is equivalent to saying we're looking for the condition that the x12 and x22 are equal and t12 and t22 are equal. So let's just call this condition x and this condition t. Alright, now the equations become x is equal to, and x11 we can kind of like read off if we wanted to. This one was 23.75. So this right here, 23.75. So 23.75 meters. And V12, coming back up here, what was V12? That was the speed that number 1 had, which is 6.5 meters per second, times time. So that is now this equation. This equation maps to x is equal to, and then again we have to look, is 16.125 meters plus 6.7 meters per second times time. Okay, this is a system of 2 equations and 2 unknowns. So we solve this system just as we would any algebra equation. For example, we might set the two x's equal to each other, and so since these two are equal, then these two sides are equal. And so what that would give us is that 23.75 meters plus 6.5 meters per second time is 16.125 meters plus 6.7 meters per second time. And so now we basically combine like terms and solve for time. So time ends up being 7.625 meters divided by this 0.2 meters per second. So that gives us a total time of about 38.125 seconds. Now, in some sense worth noting is that this is how much time it takes from the second part of the motion. And so if we want to get like total time, we have to add back the 2.5. So the total time is this plus 2.5 seconds, or in other words t plus 2.5 seconds, which is about 40.625 seconds. So that's how much time elapses before one catches the other. We could also ask like what's the distance, so we can plug in for t to solve for x. And that distance would now be the distance in this equation, in either of these equations. That'd be the position relative to where the first guy was. So this is going to give you the distance, where the second guy is. So it's going to give you the distance that the second guy travels to catch the first guy. If you then subtract the 7.5 meter leader, you've got how far the first guy travels. So that's all for today's video. It ran a bit long because I tried to do both examples. Hopefully you learned something from watching it, and as always, thanks for watching.